All right, so today our topic is going to be focusing on roots of unity, which is what we first introduced each other to in our last lesson. So what we're going to be focusing on today, we'll do a bit of a recap just to make sure, we're still kind of on the right page with our roots of unity. Then we're going to look at an example that will help us derive an interesting geometric result. So today's lesson is about thinking about some of the applications of roots of unity and why it's a worthwhile thing to do. So maybe if I just, to start with, write the formula that we typically deal with roots of unity that hopefully is familiar from last lesson, z to the power of n equals 1. Now in theory we do plus or minus 1, but we're just going to stick with 1 just to ease into it for today. So here I've noted out a bunch of things that I guess we need to make sure we're comfortable with before we dive into this example. So feel free to yell out as these jump to you, but does anyone remember why we call it roots of unity? What's the reason for this name? Anyone? You at the back? V? No ideas? Mary, any ideas why we call it roots of unity? Yeah, because we're dealing with the number 1 here, and you can think of 1 as kind of like the unitary number. It's the number that can represent a unit of something, 1. So we call it roots of unity because generally we're trying to find the solutions to this equation. And as you may remember back when you were learning quadratics, however many years ago, sometimes we'd refer to those solutions as the roots of the quadratic. So that's kind of where these words come from. Does anyone want to guess what these letters stand for? Something, something of something?
Fundamental Theorem of Algebra.
Fundamental Theorem of Algebra, very good. And what's the deal there? Why is that useful to us today on roots of unity?
To find out how many roots you have by looking at the expression.
Perfect. So if we've got z to the power of n equals 1, if I pick a value of n, which is what we normally do, let's just say I pick the value 8. Z to the power of 8 equals 1 will have how many solutions? 8. Perfect. So this theorem really helps us to know kind of what we're dealing with and always act as a check so that when we work through our procedure we can say, all right, I need to have 6 solutions. Did I get 6? What is something that we know will always be a solution to this equation?
1.
1. And why will 1 always be a solution?
Because 1 to the power of anything is always 1, and so if z is equal to 1, then
perfect. Exactly, thank you. So it's, I guess, important to remember that even though z is a complex number here, 1 can still fall within that realm of complex numbers. It just basically means it's 1 plus 0i. So yes, 1 will always be a solution, so another little check there. If we don't get 1, something's gone wrong. What about these two words? Anyone want to guess what they might be about? What's something we've learned first when we were first getting introduced to complex numbers? What was the phrase we learned? Something, something in relation to complex numbers. Any guesses? I'll give you a hint. The second word, the first word, sorry, is complex.
Complex conjugates.
Complex conjugates, very good. And the reason that's, I think it's conjugates. The reason that's relevant here is because it can act as another check. When we start to plot these in the Argand diagram, which you may remember from last lesson, we can be confident that the non-real solutions will be complex conjugates, which means they sit vertically above and beneath each other, so that if that doesn't happen, chances are something's gone wrong. Now, sticking with the Argand diagram, and noting that because we're dealing with 1 here, we end up with a unit circle. What do we know about our n solutions, however many there are? What do we know about how they'll look around that unit circle?
They're equally spread out.
Equally spaced, beautiful. So that's another visual check. If we get results that don't look equally spaced, maybe something's gone wrong. And then finally, before we go into the procedure, there's one other set of words that I think are going to be relevant to us. Now, when we plot our equally spaced solutions, around the unit circle, if we were to join them up, what do you think we will end up with? Anyone want to guess? The first word starts with R, the second word O. I'll give you a hint for the second word. The second word is polygon. What kind of polygon do we get when we join up all of those equally spaced? A regular polygon, that's right. Do you remember what a regular polygon is?
The shape of which each side has the same length.
Same length, perfect. So if we end up with 3 points, it'll be an equilateral triangle. If we end up with 4 points, it will be a square. 5 points, a regular pentagon. All the sides will be equal. And the other thing that we can know from it being a regular polygon is that all the interior angles at the origin will also be equal. So they're the key things to keep in mind. Obviously, I'll leave that up so that we can always have it as a reference. Now, in terms of the actual procedure, which is what we covered last lesson, I've noted it up as basically 5 steps that we can follow. So part of this activity will be giving you a bit more practice on these steps, but also with the idea of seeing how it can lead to some interesting results. What's the first step? What do we let z equal to help us deal with this equation? Does anyone remember?
Voids are complex numbers.
Yeah.
Can we put it as x plus iy?
Well, you could. Certainly, one way of thinking about complex numbers, and I'll write it over here, is we let z is equal to x plus iy. Does anyone remember another way that we learned very recently of complex numbers? There's actually 3, but for now you've only learned 2. What was the other way?
Oh, the one with the cos and sine.
Yeah, so instead of x and y, we did a bit of work to see that actually that could be cos theta plus I sine theta when we're dealing with everything having a modulus of 1, which is called the mod arg form. Yeah. Now this is actually the form that's going to be most helpful. So I'm just going to write, we're going to let z equal cos theta plus I sine theta, where theta is the argument, basically the angle that the complex number makes with the real axis, the positive real axis. Any guesses why that form helps us? And again, it's because of something we learned recently. I'll give you a hint. DMT. Anyone remember what that stands for?
The De Moivre's theorem?
De Moivre's theorem? Yeah, that theorem where we kind of learned it using induction. We proved that when we have our mod arg form, when we've got z to the power of n equal 1, we can actually, if I kind of continue over here, z to the n would be cos theta plus I sine theta to the n. And according to De Moivre's theorem, we can therefore say that's cos n theta plus I sine n theta. So we bring the power into the angles. So what does that mean? If we've got z to the power of n equal to 1, what do we know about our angle, in this case, n theta? What would n theta be? And this kind of goes back to the kind of trigonometry you would have learned many, many years ago. But it kind of is about, maybe just for now, I'll say, if we know that cos theta plus I sine theta is equal to 1, let me draw up, maybe I'll start with the sine curve. And then beneath it, I'll draw up a cos curve. And this is 1. If I want cos theta plus I sine theta equal to 1, what do I know straight away? Is 1 real or complex? Well, it's kind of technically complex, but there's no imaginary part, is there? So what do I know about I sine theta? It's 0. So what do I know about sine theta? It has to be equal to 0, right? And we know kind of in the domain we normally care about, there's 2 points where that is. Now, those 2 points happen to coincide, one with -1, but one with 1, right? And because we know that these are periodic, and actually here as well, we're going to have 2 solutions. Actually, is that right? Yeah, 2 solutions where the the cos part is what we need, 1, and the sine part is what we need, 0. And we know that if we keep going, it will keep repeating, right? So what do I know about these 2 points here? That's 0, that's pi, and that's 2 pi. What do you remember? Is this ringing any bells from anyone for the last lesson? I know that the angle that I care about will be, well, I know 2 pi is an answer.
It's going to be multiples of 2 pi.
Yeah, any multiple of 2 pi, noting that 0 is kind of also a multiple of 2 pi. And the way we reflected that is we put a k here, and we said k is basically any integer. So we know that we're going to get what we want when n theta is 2 pi k, and then we just kind of did the simple rearrangement to say that means theta will be 2 pi k all divided by n. That's kind of step 1. So then we want to find the values of k that exist in a certain domain. Does anyone want to guess what that domain is?
Negative pi and pi.
Yeah, and what was the idea behind that? Because that's not the most intuitive way to think about it.
Well, you said that because it's like easier to find the other ones, like the conjugate.
Yeah, it's kind of linking back to this idea that we know we're always going to get, for the non-real answers, complex conjugates. Thinking about the domain in this format, which is kind of the same as thinking about it, the full 2 pi revolution, just one going one direction, one going the other, it helps us make really clear or very easily see the complex conjugate pairs. So that's why we do that. So once we find those values of k in this domain, we sub them back into our formula for theta. So we'll get 2 pi times something on n, like 1 or 2 or 3 or whatever they are. And then we can use those angles to plot them on the Argand plane. That's basically the procedure. Any questions? Everyone happy?